Hi, I'm Dana Moshkowitz, and I'm going to speak about the reduction from non-unique games to Boolean unique games. This is joint work with Ronen and Eldan. Okay, so here's a big picture of this work. If we want to prove the unique games conjecture, we need to show a reduction from a problem that's known to be NP-hard to unique games. In 2016, Subhash Kot and I had a paper where we suggested to focus on the Boolean version of the unique games. And then we showed a candidate reduction from a known NP-hard problem, a problem that we showed was NP-hard a few years before that, to Boolean unique games. Okay, and I should say, in our mind, Boolean unique games, hardness of Boolean unique games already captures the heart of the unique games conjecture. However, to get the full unique games conjecture from the Boolean version, you need to do what's called strong pair repetition of unique games, which is an extremely fascinating problem. Lots and lots of tweets. It's a very interesting story, but it's not this work. So we won't talk about it more here. Okay, so all we want is to prove hardness of Boolean unique games. There is a reduction. Let me say that the reduction from 2016 had some problems. For one, it wasn't a polynomial time reduction. It was an exponential time reduction. And the idea was that it would rule out, right, it's like not to do the end, but slightly better. So it would rule out polynomial time algorithms for Boolean unique games, assuming that SAT requires exponential time. So this is one disadvantage. Another disadvantage, well, there were some concerns about whether it was actually sound or not. It was just a candidate. We didn't prove correctness. And even though this reduction has the ideas that we believe should prove hardness of Boolean unique games, we did make one technical choice, specifically for anyone who knows, using periodic half spaces instead of half spaces. And this technical choice seemed a bit fishy. There were concerns about whether the reduction can be some because of that. So this is it. This was 2016. Actually, already back then, Ronen and Dan and I decided that we'll try to analyze this reduction or a similar reduction. And the result is this work. So we do two things. For one, we take this reduction, the 2016 reduction, and we figure out how to do it right. As in, we outline a reduction that is actually polynomial time. So it's actually an NP hardness reduction. And we get rid of this periodic half space. We just use half spaces for encoding. So this seems like really clean and reasonable and very likely to be sound reduction. Okay, so this is one contribution. We actually get this the old reduction right. The other contribution is we actually managed to prove soundness. Actually managed to analyze the reduction, but not quite the original reduction. Instead, what we do is we come up with a new game, with a new problem that we wish was NP-hard. It's similar to problems that are known to be NP-hard. But we don't know how to prove NP hardness. We do know how to rule out. We know that semi-definite programming-based algorithms won't solve it. But we don't quite know how to prove NP hardness for it. But for this related problem, we're able to take a reduction that is analogous to this 2016, the candidate hard unique game. And we are able to analyze this reduction from this wish for NP hardness to Boolean unique games. Okay, so this is what this work is about. Here's what I want to do in the talk. So one thing is the first thing I'll do is I'll take Boolean unigames, and I'll explain to you Boolean unigames, right? So I'm going to define this Boolean unigames conjecture, right? So this is the first thing. Second, I'm going to talk about NP-hardness results. So what's known? So I'll talk about some of the strongest PCP theorems that there are. So I'll talk about specifically the PCP theorem that is in this, 2016 reduction. And this will set the stage to talk about this wishful PCP theorem that we need. And finally, I'm going to talk about the main technical component in the analysis of the reduction. So there is actually a mathematical theorem, a new concentration theorem that is, in my opinion, of completely independent interest. And I'll talk to you about that. Okay, so this is the plan for the talk. Of course, right? The overall point of the talk is that now we did that, right? The next stage is to actually bring back the reduction to be a reduction from a known NP-hard problem to Boolean unigames, and eventually prove the Boolean unigames conjecture. Okay, so let's do it. The first thing is, let's talk about the Boolean unigames conjecture. So really, this is a problem about max cut. Max cut is like the basic unigame. So you're given a graph, and the task is to partition the vertices into two, such that there are as many edges as possible that cross the cut. And the case that we'll concentrate on is the case where there is a cut that almost all the edges cross. So 1 minus delta fraction of the edges cross it, and you need to find a cut that also crosses most of the edges. Okay, so this is this picture here. Almost all the edges cross except for this red edge. Okay. So to tell you what's known about this problem, I have this scale on the right. So this axis is for the fraction of edges that you cross. Okay, so we know that there is a cut that crosses 1 minus delta fraction of the edges, and the question is, how many edges can we cross? Okay, let me just mention, right, why this is a unigame. You can think of every edge has a constraint. Right, so every vertex is supposed to get a bit. Are you on one side of the cut or the other side of the cut, 0 or 1? And every edge wants its two endpoints to have different signs or different bits. Right, so if you know the bit on one side, you know what's a bit on the other side, and vice versa. Okay, so this is uniqueness. The endpoint, the assignment to one endpoint dictates the assignment to the other endpoint. Okay, so this is the basic unigame. Okay, so let's go back to our axis. What's known about this max cut problem? Okay, so for once, so right, as usual, right, if there is no gap, so the first question is, suppose that there is a cut that 1 minus delta fraction of the edges cross, and you're trying to find a cut where 1 minus delta fraction of the edges cross. This is known to be an NP-hard problem, right? So there is no gap, right? This is an exact NP-hard problem. And the question is, what happens as you kind of grow a gap, as the gap grows more and more, as you ask the algorithm to do less and less, right? The number of edges to call, the truth cross is smaller and smaller, right? The problem becomes easier. So the question is, when does it cross to being easy? So here's what's known by work of Hastad, Huang, Manokaran, O'Donnell, and Bright. We know that even though there is a cut that is 1 minus delta fraction, has 1 minus delta fraction of the edges, you'll be able to find a cut. The problem of finding a cut where the 1 minus 11 over 8 delta fraction of the edges cross, right? This is going to be an NP-hard problem. Right, so we have some NP-hardness result here. There are good reasons to think that this could this could be improved to 1 minus 2 delta, but At this very moment, this is still unknown. Okay, what about algorithms? So there is the Gomans-Williamson algorithm. The Gomans-Williamson semi-definite programming based algorithm would manage to find a cut that crosses 1 minus square root delta, fraction of the edges with a very specific constant here in front of the square root delta. And now notice that there is this big part here in the middle where, well, we don't have results, right? There is no algorithm, there is no hardness. What there is a beautiful work of Kott-Kindler, Mosel, and Ronen that shows that if the unique games conjecture is true, then the Gomans-Williamson algorithm is the best you can do. Okay, so beating it is NP hard. Okay, so we think that the hardness should extend all the way to the 1 minus square root delta regime, but it's not known, and this is where this Boolean unique games conjecture comes in. So here's a conjecture for any large constant, right? 1,000,000 for any sufficiently small delta. It's NP hard to distinguish between 1 minus delta versus 1 minus C delta, right? 1 minus delta versus 1 minus million delta. So this is NP hard, right? So this is the regime that is somewhere in the middle, right? We're not even asking for, you know, the result that we think is true is to beating Gomans-Williamson is NP hard. We're saying, okay, let's just show NP hardness of 1 minus delta versus 1 minus large constant delta. Right, so this is an easier regime to work with. And if we pull off this strong repetition for unique games, this is the only thing you need, right? So if you prove that, you'll get the full unique games conjecture, right? So this is why we concentrate on this question. Well, okay, next. So the next thing I want to talk to you about what are the NP hardness results that are known. So what can we reduce from? And I want to start with projection games. This is the foundation of optimal inapproximability results. Basically, all the optimal inapproximability results that we have start with projection games. Unique games are further strengthening of projection games, right? So this is a very important object in approximability. Now, PCPs can be described in the language of two-prover games. So this is what I'll do. Okay, so here is a two-prover game, or rather a pattern for two-prover games, a family of two-prover games. There are two provers or two players, player A and player B. Each gets a question, and each should return a vector, right? So think of it as vector of bits. So there is a vector U you get from A, vector B, V that you get from B, okay? So for concreteness, you can think of maybe we have some SAT instance, some formula that we want to figure out whether it's satisfiable or not. And we ask player A, oh, can you give me the assignments for these variables? And you ask player B, oh, can you give me the assignment for those variables? And maybe the assignment to A, the variables that A is given spend some tests. The assignments of player B spend some tests. And usually what you do is you have an overlap between the set of variables that you give to A and the set of variables that you give to B. So you'll be able to compare them. You can make sure that they're consistent. And if they're consistent, it makes sense that there is actually a global assignment that satisfies the formula, okay? So a projection game is a game in which the verifier does exactly two things. First, there is some predicate, it checks on each vector, right? So this predicate would be like, okay, is this a reasonable assignment? This is a satisfying assignment to those variables. Maybe those variables spend some constraints of the SAT formula and you'll check those constraints, okay? So on each vector, you're allowed to check whatever you want. But then the only thing you check between vectors is you check that they're the same on some subset of the bits. Okay, so there is some subset of the coordinates in U, some subset of the coordinates in V, and those should be exactly the same, right? So think of it as the assignments to the overlap in the set of variables we ask about. Okay, so this is what's known as a symmetric projection game. Right, it's projection because you take the vector and all you care about when you come to compare, you project into this overlap and you check whether the overlaps are the same. Okay, good. So these are projection games. And for projection games, we know extremely strong hardness results. So let me define the value of the game as the maximum over all possible strategies of the players of the probability that the verifier accepts. And the PCP theorem says for any epsilon larger than 0, it's NP hard to distinguish whether the value is 1 or epsilon. Okay, so even if you know that there is a strategy for the players that makes the verifier always accept, it's going to be NP hard to find a strategy that makes the verifier accept with probability even just epsilon. Okay, this is true for any epsilon. So the gap is as large as it can be. It's a gap that approaches 1. Okay, and epsilon can even go down to 0 with n the input size. So we know this ridiculously strong theorem. Let me also mention, if the predicate that the verifier checks on each vector separately is linear, then we also have this gap 1, but we need to change the completeness, so it's 1 minus delta versus epsilon, because for linear games, to check whether it's fully, if there is a strategy that is fully satisfiable, then you can just find it by solving linear equations. Okay, but there is hardness for distinguish between the value is very close to 1 and the value is close to 0. Okay, so we basically have everything we want for projection games, but this theorem can be even strengthened even more. So the big strengthening came in 2018. This is the 2-to-2 theorem. Alternatively, you could call the 2-to-2 theorem the giant overlap theorem, because this is what it says. It says that you can still get this super strong 1 minus delta versus epsilon hardness result, even when the overlap between the two players is gigantic. So even when the overlap reveals almost all the information about the vector. So given the overlap, there are only 2 options for you. Also, given the overlap, there are only 2 options for V. This is why it's called 2-to-2. Even then, there is still this gap 1 between the 2 players. Okay, so this is this amazing result. This is what's known about projection games. Okay, now towards the endeavor of proving the unigames conjecture, proving hardness of Boolean unigames, Subhash and I suggested to consider projection games over the reals. The big change is that now the 2 vectors that the players return are no longer vectors of bits, they are real vectors. Okay? And the thing is that we were able to prove an NP hardness result that's very strong, even in this case. So here's what we proved. This is was published in 2011. It's NP hard, given that there is a strategy. Well, for one thing, the vectors are well spread, right? So they have some norm, and the norm is spread over all the coordinates nicely. So, right, for sort of regular, so there is this sort of regular strategy for the players that the verifier accepts with probability 1 minus delta. Even then, if you are trying to find, if you're an efficient algorithm that tries to find a strategy that does well, right, you're in bad shape, because it's NP hard to find a strategy where the difference between coordinates in the overlap is even just square root delta, right? So here, the difference, this is the big difference from the discrete case. In the discrete case, right, it's all bits. So either you have exact equality or you have inequality. That's it. This is a much, much finer question. Here, we let the algorithm get within some small quantity, right? So the two coordinates, right, in the overlap, right? It doesn't have to be exactly the same. It can differ a little. And right, so this makes the life of the algorithm much easier. So proving an NP hardness result becomes harder. But we proved an NP hardness result. So the best algorithm, so the best algorithm that we know is this semi-definite programming based algorithm. Right, naturally you can write a semi-definite program for this problem, and you're able to get within square root delta, right? This algorithm would be able to get within square root delta in the respective coordinates. Why square root delta? Because what you're going to do is you're going to minimize the expectation of the difference squared. And you know, because there is a strategy that does so well, you know that this expectation of the difference squared is at most delta, right? If the norm is, say, 1 something. Right, so you can get this delta for the square, which means that you can get square root delta for the difference. And what we showed is that this is best possible. Okay, so if you're trying to do better than that, this is already going to be NP hard. Okay, so there is always going to be at least a difference of square root delta in the overlap. Okay, so this is what we proved back in the day, and right, with the idea of using it as a starting point for this hardness reduction. And indeed, the hardness reduction from 2016 starts with this sort of, right, maybe it's written a bit differently, right? But basically this sort of hardness result. Okay, and let me say, I think that this sort of hardness result should be the starting point for an eventual reduction to Boolean unique games. Okay, but we're not able to analyze right now a reduction from this problem to Boolean unique games. Instead, we consider a different problem that is similar, that you'll see that it has some similarity to this problem, some similarity to the 2-to-2 type game. Okay, but it's different. So let me define this new problem that we consider. We call it the subspaces near intersection game. So here is how it goes. Again, it's a two-prover game. You have two players, player A, player B. Each player gets a linear subspace in R K. Out of the K, think of K as a large constant, right? This is always the case in those problems. Like the vectors are constant dimensional for a very large constant. Now, the verifier, when it picks those two linear subspaces, it has, right, they're correlated. They're correlated, and also it has in mind some hyperplane in R to the K. Okay. Now, each player should respond with a unit vector in its subspace. Okay, so again, you have U and V. Now they're real vectors like we had before, and they need to fall in subspaces. So this means, right, this is a projection game, right? Because we have some predicate, right? The fact that U is in S or V is in T, right? That there is some linear predicate that we're trying to enforce on each vector separately. And what the verifier does is it checks whether the projection of U and the projection of V on the hyperplane are the same. Okay, this is it. This is the game. And here is what you can do with a semi-definite program. Suppose that there exists a strategy that the verifier accepts with probability 1 minus delta, which is a very strong assumption. The thing is that an algorithm can only efficiently guarantee a square root delta difference, L2 difference between the projections, right? Exactly for the same reason that we had before. And our conjecture is that this is tight. So if you're trying to do better, no, it's going to be NP hard. Okay. So this is our wishful NP hardness. And under this, right, from this, we can do a reduction to Boolean unique games. Okay. Okay, so I'm not going to show you the reduction. I'm not going to show you the analysis of the reduction. This is just a topic for a longer talk. And I should say that I gave longer talks on this work and they're available online. So if anyone wants to see the description of the reduction and the analysis, you can do that. But I do want to highlight this one big component, the most difficult component in the analysis of the reduction, because I think that this is of independent interest for a bunch of reasons. So here it is. So it's a new concentration theorem for the low degree part of the real function. Okay, so here is the theorem. Fix the degree, right? So even degree 1 is interesting, but you can fix degree median. Take a function, a real function. Here it's defined over the sphere. There is a technical reason why these are easier to work with. It doesn't matter much. And in fact, in the paper, we actually need them over R to the K. Yeah, right, it extends. The function has bounded to norm. Okay, now pick a random hyperplane. So this is the hyperplane. You just pick this vector that is orthogonal to the hyperplane. And now you can look at the function only restricted to the hyperplane. So this is f restricted to h. And right, this is a local view of the function. Now for this local view, you can ask what's the low degree part of this function. So this is what's written in the beginning here. Next, you can ask about the global view. So you take the global function f, you look at its low degree part, and then you restrict it to the hyperplane h. And what this theorem says is that those two functions are closed in L2 sense, right? So think of if the degree is 1, maybe this is a vector, the vector of coefficients of the linear part, this is the vector of the coefficients of the linear part. Those two vectors are incredibly close in Euclidean distance, close up to 1 over k. There is some dependence on d. We think of d as constant, so we don't care about the dependence on d. And I should say this is tight, right? This is the ultimate theorem to prove in terms of the deviation. If f is a half space, indeed, you're going to have a 1 over k deviation. Let me say that, right, you can do a sort of Fourier analysis type technique. So Fourier over the sphere, this is called Gegenbauer analysis. You can write over Gaussian space, it's called Hermite analysis, right? So the polynomials you take for the basis are different, but kind of the spirit of the thing is the same spirit. So you can do this sort of Fourier type thing to prove some concentration result, but this would give you deviation of 1 over square root k, simply because you'll be analyzing the square of the distance rather than the distance. And this is just not good for us. This is completely meaningless when we talk about Boolean unique games, exactly because the whole thing is whether it's 1 minus delta or 1 minus square delta. And you should think of the delta as 1 over k here. So this, right, the kind of standard techniques would have given you this, and to get the actual tight result was extremely challenging. And the way we ended up doing that, well, for one thing, we talked to Boaz Klautag, and he told us about this interesting technique used in the past, say in a paper with Oded Regev, where they talked about sampling function, how you have a function, it has some expectation, how does its expectation look on a hyperplane, right? But there is a big difference between sampling and what we need to prove here, right? Between just maintaining the expectation versus maintaining the entire degree part. But the technique is you use Schur's lemma from representation theory. And what Schur's lemma tells you is that you can look at the second moment of this difference, and it actually doesn't depend on the function, it only depends on the spectrum of the function, okay? So this says that without loss of generality, you can just think of functions in 2 dimensions and work there. Even this problem in 2 dimensions is very challenging, and it ends up being solved with very careful geometric analysis. So this is what we did here. Let me also mention, right, this is what in theoretical computer science we call a low degree testing theorem, right? What's a low degree testing theorem is like you look locally at the functions, the function there maybe is close to low degree. What can you say about the function being close to low degree globally, right? If you can say that, yeah, it must be close to low degree globally, then you get yourself a low degree testing theorem. So this implies, this concentration theorem implies a low degree testing theorem. And this is a completely different technique to prove low degree testing theorems. Basically by generalizing in a highly non-trivial way sampling theorem. Right, so it should be interesting to see whether generalizing sampling should be even more useful for low degree testing theorems. Anyway, so let me end here. And this is it. Let me just go back quickly to the main picture. This is the main picture. Right, we did this reduction from the subspaces near intersection problem to Boolean unique games. This is a correct sound reduction, and the hope is that we'll also get to do this reduction. Okay, thank you.